All right, it looks like we have a pretty full house, so we'll go ahead and get started. Hello, everyone. My name is Jim Shaw. I'm the Director of Sales and Marketing at DTS. Thank you for joining us today as we continue our effort to inform and educate our customers and partners. Today's event is the first of a two-part webinar series titled Principles of Dynamic Data Collection. Before we get started, I'd just like to cover the format and a few logistics. The webinar will be a slide presentation in audio from the presenter only. All attendees will be muted, but please make sure to check that the slides are visible and that you can hear the presentation. We encourage you to submit questions throughout the presentation by typing them in the Q&A window. You should see a button at the bottom of your screen. We'll have a panel of experts monitoring and answering questions throughout, and we'll try to answer as many of the questions as we can along the way. We'll also compile all questions and answers to send out to everyone as a follow-up after the event. The session will be recorded and made available to you to share after the event. Note that anyone registered for part 1 of the series will automatically be registered for part 2. And we'll also have new participants who can still register for part 2 as well. If there's a specific topic that you'd like to cover directly in a private meeting, please reach out afterwards and coordinate with our sales team. Your presenter today is Mike Beckage. He is a DTS co-founder and CTO. Also on the line, monitoring questions and answers, are Steve Pruitt. He's our CEO and also a co-founder, and Kate Martin, who's in application engineering and leads our support effort in Europe. So with that, I'll hand it over to Mike to kick off the webinar.
Well, thank you, Jim, and good morning, afternoon, or evening to you wherever you are in the world. Thank you so much for tuning into this webinar. This is, as Jim said, this is the first of a two-part series. Today, I'm going to cover a list of topics that includes a very brief introduction to DTS and data acquisition. We'll talk a little bit about DAS theory and have an overview of what a DAS system is, a little about sensors and how they work. This is a fundamental knowledge set for anybody who's actually collecting data in the real world. Then we'll talk a little bit more about the key elements in any good data acquisition system, going on through entering that data into the software, and then an overview of what it takes to specify a proper system. Then finally, I'm going to wrap up with a very quick overview of the DTS Help Center that allows you to download and all sorts of documentation and helpful information from our cloud-based system. So the company profile is that it was founded by myself, Steve Pruitt, and Tib Kippen in 1990. We're 3 engineers working in testing, the automotive and aerospace and forensic realms. Our headquarters is in Seal Beach, California. We have a technical center with 11 people in Michigan, 7 international offices, and support staff located in 8 time zones. We have over 100 people out there to serve you. And our global technical support team, who are the engineers 100% dedicated to technical support, are shown here on the screen. We have a total of 13 people, again, spread around the world in 8 time zones out there to help you. So I'm, as the CTO of support, I'm in charge of the worldwide technical support team. And these folks and I work very close together on making sure that you're getting the data you need accurately and hopefully painlessly. If you're going to do any kind of critical test, and this includes destructive testing in automotive, biomechanics, aerospace, product testing, you know, really the time it takes to set up and build up a test and the effort expended to get to that, those few milliseconds that really matter are critical. And, you know, we like to think of this as a scenario where failure isn't an option. And so all of our products, from the data acquisition line to the data logger line through the sensors we offer for this market, are 100% tested in a shock and vibration environment and designed to get the data every time. Okay, so let's get into the real meat of the presentation here. The first thing you need to do before you do set up any data acquisition system is you should have a good handle on what success means before you start a testing project. And what does that really mean? Well, how's your data that you collect going to be used to, for example, show compliance against a performance requirement, or help solve an engineering problem, or satisfy your or some other customer's requirements? And this can be everything from crashing a car to determine the relative safety for the occupants, to building a bicycle that won't break when it is ridden over hard terrain. And then you need to think about, how will you really judge? What are the metrics for having done a great job? So I like to think of this, the main steps to success at the very top level are: start with doing your homework. In other words, understanding what you need to deliver when your testing mission is complete. Make sure your goals are clear. Ask questions for the end user of the data, for the engineer you're working with. Make sure the goals are clear. And what we're going to really focus on here today is understanding the equipment you are working with. If you've got clear goals but don't understand how to implement that in the equipment, then you're not going to get very far. And finally, you need to pay supreme attention to details. My wife used to say that that was one of the main missions she tried to drive home to the third graders she taught for 30 years. There are many standards and recommended practices that apply to the testing world. If you're working in automotive, aerospace, or biomechanics, safety-related applications, there are a number of SAE and ISO recommended practices that govern many aspects of the instrumentation job, everything from the electronics and the sampling, transducers, sign conventions, and so on. So part of doing your homework is not reinventing something that's already been invented, and making sure you're aware of the standards and recommended practices that apply. A key recommended practice in our world is SAE J211. It's also known as ISO for International Standards Organization 6487. And this is instrumentation for impact test. Part one is electronics. Part two is actually imaging. So if you're taking images, high-speed images of a test, this also applies to you. Very important. And this is only one of many, but one that we rely on heavily. A sample of the kinds of things that are specified in the recommended practice are things like the amplitude response corridor. If you're going to collect dynamic measurement data, and we see frequency on the x-axis and amplitude on the y-axis, your data must fall into this corridor if you're going to collect data in accordance with the recommended practice. So this is one of many, but just an example. So let's talk a little bit about DAS theory and an overview of what a DAS system is. You can represent any data acquisition system very simply, as I've shown here, with only 4 blocks. This applies to all data acquisition, not just DTS products, but anybody who's making measurements needs to start with transducers. And the transducers are devices which transform one type of energy into another. And in our world, they're converting a physical parameter such as force, velocity, acceleration, strain into an electrical signal. Many different technologies and many different properties exist in these transducers. And if you're going to have accurate information, you need to calibrate both the sensors and the data acquisition systems. The first step, or the first element in a data acquisition system, is what I refer to as the sensor interface. A long time ago, we used to call this the signal conditioner, but as electronics has gotten more complicated and added a lot more capability, it actually is much more than that. But fundamentally, it converts a sensor output into a usable signal that can be stored for later processing. The key circuits in a sensor interface are an excitation source, which is a fancy term for power supply, amplification, because signals are small and need to be increased in amplitude. Sensors aren't perfect, and so we need to have what's referred to as offset removal. And filtering. Sensor signals are inherently noisy for a number of reasons, and for a variety of reasons that we'll cover later in the series. Filtering is extremely important. And then any decent system, any good system these days, will have a lot of self-test features. So once we have a usable signal out of the sensor interface system, we then need to convert that signal and store it. And today we use analog to digital conversion. And what this means is we're taking a constantly changing analog signal and we're converting it into binary digital bits that then gets stored in memory. In the old days, I'll call it, when I started, we used to use tape recorders because we didn't have microprocessor-based systems, but that technology is pretty much obsolete at this point. And finally, a modern system is going to employ a laptop, a desktop, some kind of PC where we create test setup information, communicate with the hardware for everything from setup, diagnostics, arming, testing, and download, and then you'll do your data processing where you calculate injury algorithms, performance data, and plot the information. My beginnings were at a crash test facility called Mobility Systems and Equipment Corporation in 1979. And on the left, that is about a 21-year-old version of me sitting at a bench that was about a 40-channel data collection system that weighed roughly, I would say 150 kilograms or 300 plus pounds to do 40 channels. And what we would do is our remote location with signal conditioning and tape recorders would be connected to a test vehicle via a long cable. We used to call that an umbilical cable. And this is the way we did it until the 1990s. You may note in the picture on the right, this is a vehicle crash test in California, and Steve Pruitt, who is also on the call, is actually on top of the barrier there. And this is a place where the three owners of DTS all worked and met. So let's take a look at a typical modern system. It starts with sensors. So we have an array of various sensor types that can be any type of physical sensor. Those sensors plug into a small unit which contains all of the features of the sensor interface system, signal conversion and storage, and a communications interface via Ethernet or USB to a laptop or desktop PC. And then we install that system onto, for example, a sled, a vehicle, a product that we're going to test, and communicate via a single long communication cable. We've come a long way, is the point of that message. And if we look at the right, that is a single channel amplifier from the 1950s using vacuum tubes. And today we have multi-channel systems that can fit in the palm of your hand that do a lot more than we could have ever done with the old technology. DTS is a pioneer in using modern technology to make tiny, high capability data recorders. So let's talk about the fundamental hardware functions in a data acquisition system. Again, we can reduce any data acquisition system to what I refer to as the signal chain. It starts with a sensor on the left. We have a power supply or an excitation source that supplies power to make the sensor work. We have an analog front end, which is typically a special amplifier called a differential instrumentation amplifier. Sensors aren't perfect, so we have offset compensation. Sensors put out small signals, so we need gain. Before we can digitize or use the analog to digital conversion, we have to have an anti-alias filter, which performs many functions, including removing noise, but also removing the likelihood of any aliasing in the signal. We're not going to talk too much about anti-aliasing today. That's actually reserved for session number 2 because it's a topic in and of itself and extremely important if you're going to collect high fidelity data. Then we have the analog to digital conversion, and finally a processor that runs firmware to manage the internal workings of the system, put data into the memory, and then communicate with the outside world. Before we go any further with data acquisition system theory and key elements, we need to talk a little bit about how sensors work. It's very important that you understand the fundamental principles underlying the operation of common transducers. And so that theory includes the concept of piezo resistance. That piezo resistance concept is applied in strain gauges, micro electromechanical systems, which are often referred to as MEMS sensors, potentiometers, internally amplified devices, and then special sensors. Wrapping up this section, we'll talk about the concept of sensitivity, which is key. Basic transducer theory. If you remember from the earlier slide, what we're trying to do is we're trying to quantify physical parameters. And so we use a sensor to do that, that is then connected to the data acquisition system. The best example I know of is a simple strain gauge. A strain gauge is a device that measures the change in shape or length of a material. And if we look at this diagram here, if we assume this is a metal specimen, for example, part of a load cell or part of a structure that we're measuring, this structure will actually change its length slightly in response to stress. So strain becomes the way we measure stress on a material. When we glue a strain gauge, shown here in the middle as the gold part, it has a zigzag pattern of conductors that, when they are stretched or compressed, they slightly change their resistance. And so strain causes the resistance of a metal or silicon conductor to change in proportion to the applied force. If we put a very sensitive ohm measurement meter, an ohm meter, onto the strain gauge, and we compress the specimen, the resistance will go down. If we put the material in tension, the material gets a little bit longer, the conductors have a little higher resistance in that strain gauge, and the resistance goes up. Again, compression means that the resistance goes down, and tension means that the resistance goes up. This is the basic principle of how we measure a lot of physical changes in the world. Stress causes strain, and then we quantify the strain. In the real world, we take a gauge, a strain gauge, which can be a single axis, a 2-axis, or a 3-axis gauge, and then we affix it to a specimen that we're trying to measure. In the case of a load cell or accelerometer, the gauges actually get bonded to flexible elements that allow us to quantify those forces. Now, the great thing about strain gauges is we can use more than one of them to make a transducer, and when we do that, we can actually, in this example on the right, if we use a 3-axis gauge, we can actually determine which direction the force is coming from if we use enough gauges. And that's how we make load cells. Enter the concept of the Wheatstone Bridge. Remember that strain gauges change their resistance, but they only change their resistance in very tiny quantities, fractions of an ohm. And so the concept of the Wheatstone Bridge allows us to measure tiny resistance changes by building a 4-element bridge as shown on the right. The 4-element bridge consists of matched resistances. We apply a large voltage to the top and bottom. We call that the plus and minus excitation. Typical excitation voltages would be 2, 5, or 10 volts. And then if we put a very sensitive voltmeter between the plus and minus signal, and let's say that one of those resistive elements is now a strain gauge, the tiny resistance changes in the gauge are going to make a measurable voltage between the plus and minus signal. So the key thing here is that the data acquisition system must apply the excitation voltage to the sensor or the bridge. The tiny changes that come out of the bridge when we excite them with acceleration or force, physical stimulus, need to be amplified, filtered, and then recorded by the data acquisition system. A key point is that the output is proportional to the excitation. The more excitation voltage we apply, the more signal we get per unit of physical stimulus. We can recreate our Wheatstone Bridge as shown here, where we still have the 4 balanced resistances, but we've now made R2 our strain gauge. So once again, our strain gauge is on a material. We put stress or force on it. It causes the length of the material to change a little bit. That change in length causes a tiny change in resistance in R2. And then, consequently, we have a small change in the signal between the plus and minus signal outputs. So, stress, meaning strain of tension or compression, causes the signal to move up or down. Now, how do we relate the output of the sensor to the engineering units we're trying to measure? This is represented by the concept of sensitivity. It's the numerical relationship that relates the physical stimulation to the electrical output. And we typically refer to that as millivolts of output per volt of applied excitation voltage per engineering unit. So it's a very simple concept. We have an excitation source, big voltage to a bridge or a sensor of any type. And when we apply a known physical stimulus to the sensor, it will then put out a signal, and we represent its output as millivolts per volt per engineering unit. This is the concept of piezoresistivity that we just talked about. And load cells commonly use several or many strain gauges glued to an object of known dimensions and connected as Wheatstone bridges. Typical load cells employ machined material posts that with strain gauges on their sides. And if we build the load cell correctly, we can then identify the forces in 3 different directions and the moments or the torques in 3 different directions. And it's important to note that load cells have a very low output, as do many sensors, typically less than 0.02 volts or 20 millivolts full scale. So it's very difficult to do anything with that voltage without proper amplification and filtering. An accelerometer can be thought of as an inertial strain gauge load cell, where we take a bending member with an inertial mass on the end of it, and we put a strain gauge on it. Now, most of the accelerometers that we use in the modern world don't use cantilever beams, but rather they're micro-machined from a silicon crystal, and we call those micro-electromechanical systems. MEMS sensors are available to measure many parameters like pressure, force, acceleration, and so on. Potentiometer. Think of this as a volume control or a variable resistor. We can wire up a potentiometer as a Wheatstone bridge. And in fact, that's what we do for things like linear potentiometers and string potentiometers to measure displacement. And these devices are used in a lot of places. Now, there's a special class of sensor that I refer to as active sensors. And our angular rate sensor is a prime example. This device uses a MEMS gyro, but there's also a lot of built-in electronics. And when I mean built-in electronics, It literally has a power supply, an amplifier, and a filter. And so it has active electronics inside. These devices typically work on a wide range of input voltages, and they have high-level output voltages. A key differentiator between an active sensor and a passive sensor is their output is not proportional to excitation. There are some special sensors. This particular one is called an IR track. It uses the intensity of light in a telescoping tube to determine displacement. They are nonlinear devices, and there are special considerations there that we'll talk about in the next, in part 2. Other special sensors include thermocouples, measuring high voltages from electric vehicles, hybrid vehicles, and so on, and the entire class of piezoelectric sensors that require special signal conditioning. So, key points: that sensitivity is the numerical relationship that relates physical stimulation to electrical output. Passive transducers usually are simple resistive bridges, and the output is proportional to excitation. Active transducers have lots of other things inside, and they have output that's not proportional to excitation. It's important also to note that there's no standard for communicating sensitivity, and so it's important that when you get calibration data from a sensor manufacturer, that you make sure that you understand that the standard format is millivolts per volt per engineering unit for a proportional sensor, and millivolts per engineering unit for a non-proportional sensor. All sensors have limitations, and choosing the right sensor for a given measurement is key to getting good data. Sensors have ranges, bandwidths, resonance points that all must be considered in making measurements with high fidelity. We're not going to get into the depths of this. It is an extremely important topic that we're going to cover in part 2. So a little hint here is that sensing devices are linear only over certain frequencies and ranges, and common sensors have resonance concerns that we need to really understand. Again, more in part 2. So let's take a look at the DAS key elements here, get a little deeper under the covers of the DAS. By review, we have a system that converts stress into strain. The strain causes resistance changes in a bridge, and we need a data acquisition system because sensors require excitation, and it's got to be stable and well controlled. Output voltages from sensors are simply too small to use without amplification. Transducer signals have to be filtered, and failure should not be considered an option, so we need comprehensive self-diagnostics every time we use the system. So a typical system in 2020 basically looks like this. You've got an all-in-one unit where you plug sensors into one side and Ethernet or USB into the other, and then we have a graphic user interface running on the computer that allows us to set up and download and look at data. So let's talk about the fundamental hardware control functions in the signal chain. Number 1, we have to know how to set the excitation. What voltage is the sensor designed to work on? What voltage was it calibrated at? Very important. Signals are very small, so we need to be able to set the gain. Typically, most systems will have at least 2 gain stages. And in the case of our systems, you can set gains as low as 1 or gains as high as over 10,000. Again, very important that the software does the right thing in processing the signals. Sensors aren't perfect, so we have an offset compensation circuit to make the output of the analog front end 0 when the physical output is, or the physical stimulus is 0. We need to set the hardware filters. We need to set sampling parameters like sampling rate, sampling duration, and the triggering methods, which also includes time alignment. And finally, diagnostic routine that manages the signal chain, commits data to memory, and allows us to communicate with the outside world. So we're going to go into some of the elements like filtering and shunt checks in greater detail in session 2. If you look at one of our user's manuals, you will see a diagram that depicts the typical signal chain with some information about the excitation sources, what gains are available, and what the bandwidth is. These are all very important points that you must understand in your data acquisition system to make proper setup decisions. Again, more in session 2. The sensor interface that the user needs to deal with is typically depicted by a connector in the middle with pin numbers, where the sensor is connected on the left, perhaps the sensor ID chip, and then the immediate connections under the connector are shown there as excitation and amplifier and things like bridge completion. In our larger system, Slice Pro, it has a lot more features in the sensor interface, and we'll talk about those in a little greater detail in session 2. I'm only going to touch on the concept of anti-alias filtering, mostly to say we must have a really good anti-alias filter that has the proper settings. We'll go into details of exactly what is aliasing and how to avoid it fully in the next session. But today we're just going to talk about the basics. Analog to digital conversion is the process of converting a continuously changing analog signal, depicted here by the red graph line, into digital representations of that signal. There are 2 main parameters we talk about. One is resolution, which is the number of bits or the number of steps on the y-axis, and the sampling rate depicted on the x-axis. The basic message here is you have to use an appropriate combination of sampling resolution, number of bits, and sampling rate in order to most effectively digitize a waveform. There are 3 types of filters used in most systems, including all of DTS systems. We have continuous time analog filters, software programmed analog filters, and then post-process digital filters that you normally do on the PC. Again, we'll cover some of that in greater detail in the next session. But the bottom line is that if you understand the sensing technology you're working with, and you understand the data acquisition system architecture, then you will be well prepared to enter all of the correct data into the data acquisition software. Shown here are all of the questions that you must answer if you're going to set up one of our systems, and this is shown in the software package called Sliceware. But you can see we need to make decisions for things like, is the transducer proportional? What's its sensitivity? What's its range? And we have a provision to say, well, what is the final frequency of interest called the software filter that we need to support? How to do shunt tests, offset removal, and so forth. So if you are familiar and educated on the DAS design and architecture, and you understand your sensors, then you can make these decisions appropriately. So let's talk about the fact that we should never assume that a data channel is functioning correctly without a cross-check. One of the ways we can do cross-checks is to implement shunt checks whenever and wherever possible. We can also apply mechanical excitation and check for reasonable response. That's why we have real-time display of data from the DAS in all of our software. And we have a lot of comprehensive self-diagnostics, so we need our users to understand the data channel diagnostic information as fully as possible. If you've got diagnostic failures, don't test until you resolve the failures or understand why they're there. For example, with an accelerometer, even a 2000G accelerometer, we can do what we call a 2G roll check. Gravity is constant, and we think of it as 1G or 1G force, some people would say. If we take an accelerometer with its active axis so that gravity is essentially pulling on its inertial element, we can rotate the accelerometer 180 degrees, and we should see a 2G shift from plus 1G to minus 1G. Very, very confidence building check. So, steps to success. Number one, understand the test requirements and standard practices in the world you're working in. Determine what measurements are needed to fulfill your mission. Determine the required data bandwidth. Remember, data bandwidth is not the same as sampling rate. Data bandwidth is what we call the frequency of interest. And that can be anywhere from a few hertz to hundreds of thousands of hertz. Choose appropriate sensors, and don't forget the resonance issues that we're going to talk about in session 2. Then you have to choose the appropriate data acquisition system, bandwidth, filters, and sampling settings. Carefully set up and monitor the collection parameters. And a concept we'll touch on again next time is undersampling. That has to do with the relationship between the sampling rate and the bandwidth of interest. And then perform any required software filtering. And if you've done all that with great care, you should be happy with a job well done. So at this point, I want to point you to our website, which is dtsweb.com. On the right-hand side of the pages on the website, you will see a tab that says Help Center. And if you click on that, you will see a screen that looks like this. Welcome to the Help Center. We have a number of helpful articles and educational materials that are available to anybody who visits our website. If you type into the search box a topic, you can look for what's available as without being a registered user. However, without registration, you can download users manuals, data sheets, and drawings, and search the knowledge base. If you register on our Help Center, you can submit help requests, attach files, download software and firmware, and protected content. So the key point is, if you register, we have to approve you to download that stuff, but it's very easy, and I encourage you to do that. The DTS support team on the Help Center consists of 24 engineers in 8 time zones. So if you've got a problem in the middle of the night, you can probably find somebody. If you go to the new to the Help Center, you will find links to help you register. And when you do that, when you are a registered user, then you can then submit a specific help request, and one of our Help Center agents will get back to you as soon as possible. To let you know, we shoot for less than an hour if possible. Less than 8 hours is generally considered something we hit pretty much all the time. So you should expect a quick response. So topics during session 2 are going to cover dealing with real-world challenges in great detail, some advanced sensor considerations, filtering and anti-alias performance in detail, implementing shunt checks and other diagnostics to help keep you collecting accurate data in your critical testing world, and not to be forgotten, proper grounding and shielding techniques to ensure the highest quality data. This concludes my presentation of slides for this section. And at this point, I think we have our panelists who have been monitoring any questions that come in. So Jim, any comments or questions we ought to answer?
Yeah, thanks, Mike. There are a few hands that are raised. If those people want to submit their questions, we have some time remaining here. We can spend that time monitoring and answering the questions. I don't know, Mike, if you want to take a look at questions and answer any live.
Yeah, absolutely. Yeah. So I'm looking at some questions that are coming in here, and there's a question about gains and how do we do that? Well, all of our high-speed data acquisition systems are 16-bit systems, and we have a very adjustable set of gains between the sensor and the A to D converter. And so when you enter things like your sensitivity and your range of measurement, the software and the firmware work together to actually adjust the hardware to the best possible gain. As I mentioned, the gains can be anywhere from 1, which allows you to measure large voltages, all the way up to a gain of several thousand. So it's extremely adjustable, and the gain is actually automatically measured. So that's an important thing, and we try to make the best use of the digital realm. I see there's a question about excitation voltages, and why do we use different excitation voltages? Thank you for that question. That's a great one. Well, it turns out that sensing technology varies a lot, and there are some sensing solutions that use very low resistance gauges. And some of these are more common in Asia, but there's actually a whole realm of sensors that have a maximum working voltage of only 3 volts. And that's why we have excitation source adjustability all the way down to 2 volts. If we go back a few years or decades, it was extremely common to use 10 volts excitation for everything. And so there's a legacy there of using a 10 volt excitation source. But starting in the late 1990s, it started to become a lot more popular and actually a really good idea to use lower excitation voltages. And so right now, the most common excitation voltage is 5. And that's really it. Sensing technology and legacy practices really go into why we have lots of different excitation voltages in use. A question about balancing accelerometers. Can we do that? Yeah, of course. We have a very sophisticated offset removal circuit in all of our products, and it actually is an automatic system that takes a measurement on the sensor and through an iterative process applies an offset correction voltage. So we can essentially balance any transducer that's functioning properly. Thank you for the great questions, by the way. These are awesome.
Yeah, and Mike, the questions that have not been answered so far, we've captured, and we will answer in the follow-up email and share with all of the attendees. So I think we're right at our end of time here for today. Very good. Thank you very much for presenting. And the next session will be on Wednesday of next week at the same time, and reminders will go out.
Yeah, thanks to everybody for participating. I sincerely hope you will come back next week for part 2. I think that we've given you a basic introduction to a lot of concepts here, but the things we're going to talk about next week are really take you into the realm of being a user with the right knowledge to make sure you get good data. So please come back.
Great, thank you.